Hello everybody, and welcome to the beginning of section 8.5. We are looking at page 112 in our workbook, and this is the beginning of the section on Taylor polynomials and Taylor series. This topic is going to give us a way to approximate functions and help us to do things like estimating the value of an integral that's not possible to calculate exactly. So let's start this discussion just with a specific example. We're going to take a function, e to the 2x, and see if we can step-by-step build a series that represents that function. And our series is going to have the following form. And to make it work, what we're interested in finding is what do these numbers, C0, C1, C2, and so on, have to be so that the series matches the function. That's kind of where we're going with this. All right, so we're going to start by giving our function a name here. E to the 2x is the function that we're trying to represent as a series. And we'll start by assuming that our series is equal to that function and just see kind of where that assumption leads us. All right, so our series looks like this. It's an infinite series, so it goes on forever, and that's going to be equal to our function. And what we're going to do next is just to take a bunch of derivatives here. Turns out that that's going to help us to figure out what these constants C0, C1, C2, and so on are all equal to. All right, so what would happen if we took the derivative of this equation? Well, if we started with C0, it's a constant, so its derivative is going to be 0. Then we would move on to C1x, and its derivative would just be C1, because the derivative of x is 1. And then C2x squared, its derivative would be 2C2 of x times x. We're just using the power rule, and so on. Okay, derivative of C3x cubed would be 3C3x squared, and we just keep going. Okay, that goes on forever. And we want to take the derivative on the right-hand side as well so that we have a balanced equation. And what is the derivative of e to the 2x? Well, if we use the chain rule, we're just going to get 2e to the 2x. Okay, and now we are just going to do it again. Take another derivative here. So if we start with c1, it's going to go away. Derivative of 2c2x would just be 2c2. Moving over to 3c3x squared, that's going to give us a 6c3x, and we keep going. Okay, we get to the right-hand side, take the derivative over there. That's going to give us a 4e to the 2x. Okay, and I'm going to do this 2 more times. I think that's going to be enough to help us find a pattern here. Okay, so if we take the derivative of equation 3, we'll get 6c3 plus 24c4x, and so on. And over on the right, we're going to get an 8e to the 2x. Okay, one more time. Take the derivative of equation 4, we're going to get 24c4, and so on, equals 16e to the 2x. Okay, so we've got a bunch of derivatives in front of us, and the question is, how is that going to help us to find these constants? Okay, well, what we're going to do is to choose a nice value of x to substitute into all of those formulas. And the nicest value of x that I can think of is x equals 0, because it's going to make a lot of the terms in our series disappear. Okay, so we'll let x equals 0 in all of the above equations. Something very nice is going to happen here. All right, so starting with the first equation, what would happen if we let every x in that equation be 0? Well, all of these terms that I'm circling are going to go away. They're going to be 0. And so all that's left on the left-hand side of equation 1 is c0, just that one number. And over on the right, we need to let x equal 0 there as well, so we're going to get e to the 2 times 0, but that's just e to the 0, which is 1. So we've just figured out what the first constant in our series is. C0 has to be 1. Okay, we're going to continue down the line here. Let's move on to equation 2 now. And if we plug x equals 0 there, all of these circled terms are going to go away. And we're just going to get C1 equals, over here on the right-hand side, this time we're going to get 2e to the 0, which is 2. Okay, and we can keep doing this. So if we go to equation 3, let x equal 0, only the 2c2 is left over. And over on the right-hand side, we're going to get 4e to the 0, which is 4. Okay, and continuing on, you kind of get the idea here. For the fourth equation, we're going to get just 6c3 left over. Over on the right, 8e to the 0, which is 8. And finally, 24c4 is 16e to the 0, which is 16. Okay, there's a bunch of statements that have to be true, and we can use those now to figure out what our constants are. That's what we were interested in. All right, so starting with the first equation up here, we can see immediately what C0 has to be. It's 1. And the second equation tells us that C1 is 2. What about C2? Well, there we do have to do one calculation. 2C2 is equal to 4. So C2, if we divide both sides by 2, would just be 4 over 2, which is 2. Okay, C3, same deal. We're going to take 8 over 6. That's going to give us 4/3. And then finally, C4 is going to be 16 over 24, okay, which reduces to 2/3. Okay, and we could go on. That's all of the calculations that we did, but we'll stop there. And what does that tell us then about this series? Well, it gives us a way to build the first few terms of it. Okay, so our series for f of x equals 2 to the x is p of x equals, and now we're going to fill it in term by term. And I'd like to scroll up just for a minute here. Okay, can we get that into the picture? Here's what p of x was. Okay, and what we've managed to do is to figure out what those constants, C0, C1, C2 are. We're just going to fill those in one by one. Okay, so p of x is C0, which is 1, plus C1x, and C1 is 2, plus C2x squared. Okay, so we get a 2x squared, and we just keep going. This is an infinite series, so we could continue if we wanted to, but that's kind of as far as our calculations took us in this case. Okay, so we found a series, at least the first few terms of the series for our function. And now what we'd like to do is to see if we can notice a pattern here that might help us to do this more efficiently in the future. Okay, so let's make an observation here. There is a pattern to these calculations. Let's see if we can see what that pattern is. Okay, well, we need to kind of look back at our work to discover what it is here. And so the first thing that I'd call your attention to is these numbers on the right-hand side of the equation. Where did they come from? Okay, well, they came from up here at this step where we were taking a bunch of derivatives. Remember how we started with equation 1, we took its derivative to get equation 2, and another derivative to take equation 3. So 1 here is just our function evaluated at 0, and 2 was the derivative of that. 4 was the second derivative, and that pattern just continued. Okay, and then we kind of come to a point of notation here. So 16 is the fourth derivative of f. For big derivatives, it gets inconvenient to write a bunch of primes. We could write f prime, 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 but there's a better way to write it if we've got a big derivative. You can write the fourth derivative like this. Okay, that 4 in parentheses just means fourth derivative. That notation is more convenient if the derivative we're taking happens to be a really big derivative. Okay, so that's our first observation. The right-hand side of those equations are derivatives. What about the left-hand sides? Is there anything special about the numbers over here? So like 24, for example. Notice that that's 4 factorial. 4 times 3 times 2 times 1. And 6 up here, that's 3 factorial. 3 times 2 times 1. And the pattern kind of continues. So if you look at this equation, what we've got is n factorial times cn is equal to the nth derivative evaluated at 0. That's kind of what all of those 5 equations capture. So what we could say is the following then, that every one of those equations has the form n factorial times cn equals the nth derivative. Remember that n in parentheses represents a derivative evaluated at 0. And we can take that equation and solve it for cn just by dividing both sides by n factorial. And so what we've discovered is a general form for the coefficients in the series that we just built. And on the next page, we will use it to write down a general formula for how you build a series for a function.